Did you know that a rectangle plus a rhombus equals a square? Think about it. We start with the properties of parallelograms. So, a parallelogram is a quadrilateral with two pairs of parallel sides. Two pairs. One pair, second pair. All parallelograms, such as FGHJ, have the following properties. Opposite sides are congruent from each other, and in our quadrilateral, we see that it's a parallelogram by the two statements here about the two sides being congruent. Opposite sides are congruent. That's one way to show a quadrilateral is a parallelogram. If we can show that opposite angles are congruent or the same, we can show that F and H are the same angle and G and J are the same angle, then we can show that this quadrilateral is a parallelogram. If that property holds true, it's a parallelogram. Consecutive angles, which are angles that are next to each other inside a parallelogram, or here, see we said F and G, we could say are next to each other. But F is also next to J. So those will constitute angles that are consecutive. So any two angles that are next to each other are a pair of consecutive angles, and they will be supplementary to each other. That is, they will add up to 180 degrees. Diagonals will always bisect each other inside of a parallelogram. So the one diagonal we indicate with the two congruent marks on either side are being cut in exact half, same way in the other diagonal is being cut exactly in half. So there are two congruent halves, which is what these statements are saying about the diagonals. If diagonals are bisecting each other, then you have a parallelogram. Let's complete this proof. ABCD is a parallelogram. So we're given that this is a parallelogram. That comes with all the properties we just spoke about. So what are the missing pieces that they might be asking us here? This is not really designed to be so much a proof to show any one particular thing. We're going to just see where the concept of writing a proof comes from and seeing what kind of elements go into it, the kind of statements we might make, and the reasons that go along with them. So again, this is not a particular formal proof, but it is designed like one. Alright, so we're just making some statements on the left-hand side that are true based on the fact that ABCD is a parallelogram. Alright, well let's see first. If I look at the first statement down here, or statements, I see that AB is congruent to something and AD is congruent to something. What do we think those are? Well, they're obviously talking about line segments. AB is a line segment. So on my diagram, if I put a little hash mark on AB, then the one that I think that they're talking about, if I think about the properties of parallelograms, opposite sides are congruent, then we're going to say that also CD, line segment CD, is congruent to AB. The other pair of opposite sides would be AD, and I'll put two hash marks there, and BC would be the matching opposite side, so line segment BC. The reason is the statement of what we just said is that opposite sides are parallel. Now we can actually do a better job than that. We can say two pairs of opposite sides are oops, I meant to say congruent. Yeah, congruent. So next, angle A is congruent to some other angle, and opposite angles are congruent here. Opposite angles are congruent would be the reason I'm putting here that angle A is congruent to angle C, and angle D is congruent to angle B. Statement C. AB is parallel to some other side, and AD is parallel to some other side. The property here is that there are two pairs of opposite sides parallel to each other. So AB is parallel to CD, and AD is parallel to BC. Next, statement D. Which angles are going to be supplementary to A? Well, A is up here, so we have one angle that's next to it in this direction, and we have one angle next to it in this direction, so it will be supplementary to angle D and also to angle B. And that makes sense because angle D and angle B are equal to each other, or congruent. For angle C, well, angle C has angles B and D next to it, so angle C is supplementary to angle D and angle B. So consecutive angles are supplementary. Next it says to draw line segment AC and BD. What are they talking about there? Okay, so next we draw diagonals AC and BD. And it says that the lines intersect at point E, so I'll input point E right here. Next, we're going to figure out what is congruent to angle BAC and DAC. So BAC will be this angle right here, and angle DAC will be this angle right here. So one thing that we can say those are congruent to would be through the idea of parallel lines create alternate interior angles. So this angle here is congruent to this angle up there, and the double arc is going to be congruent to the double arc that I just put in there. So we just need to name those angles. So BAC is congruent to DCA. And DAC is congruent to BCA. Alternate interior angles are congruent. Alright, one last statement. So AE is congruent to something, and that something is the other side to it, EC. In the same way that DE is congruent to BE, and that is an indication. So what we'll do is we'll mark that like this and like this, and that's an indication that the diagonals bisect each other. And so what we've done here is really just displayed all the properties of parallelograms. Once you know something is true, or something that's true, like a parallelogram, any one of these properties could show that a quadrilateral is parallelogram, and once you know it's a parallelogram, all of these properties apply, so you could use those in a proof. Time to do our first real proof, and really we're going to be filling in some missing pieces here. Let's read what they give us, let's take a look at the diagram, and mark anything that we may need. Given parallelogram ABCD, that little symbol there stands for parallelogram, so we are given a parallelogram. Within this parallelogram, DE and FB are congruent to each other. Now that has not been marked on our diagram, so we'll do so now. DE is congruent to FB. One thing you'll see we're doing here is we're going to go through and prove some things focusing on triangle proofs. So even though we're dealing with quadrilaterals, triangle proofs come up quite a bit. So just to refresh our memory, for triangle congruence reasons, we have 5 different criteria that might work. Side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse leg. So what are we trying to prove here? First, prove that those 2 triangles I just highlighted are congruent to each other. Next, after that, prove that angles 1 and 2 are congruent to each other. Alright, well, the first part is that we were given parallelogram ABCD, and that statement was made, and our reason was that it was given. We do have another given statement, but that comes down a little bit later in the mix here, where DE and FB are congruent. We mark those in the diagram. Fill in the missing pieces here. AD is congruent to some other piece. So where's AD? AD is this segment right here, and if I were to guess, well, not really guess, but use the properties of parallelograms, opposite sides are congruent. So BC is congruent. Opposite sides are congruent. Next, angle D, right here, is congruent to some other angle. We know that's going to be angle B, and so the reasoning that we would state for that is that opposite angles are congruent in a parallelogram. Bam. Number 5, we have to figure out what other statement we need here. Well, if we look at our triangle, we have enough evidence to support one of these cast of characters. And if I look closely, the one that we get here is side, angle, side. SAS. So triangle DEA is congruent to triangle BFC by side, angle, side congruence. Last but not least is to say why those 2 angles 1 and 2, why are they congruent to each other? Well, angle 1 is congruent to angle 2 by something we call CPCTC, which merely stands for corresponding parts of congruent triangles are congruent. Or just CPCTC. Let's try another one. Parallelogram ABCD is given. That means that AB is congruent to CD because opposite sides are congruent. I know that AB is parallel to the same one, CD, because opposite sides are parallel in a parallelogram. Angle CAB is this one, is congruent to its alternate interior angle buddy, which is up there. That would be, we can call that DCA. And we would say alternate interior angles are congruent. We have that angle AEB. Let's find that one. A to E to B. This angle right here would be congruent to, you guessed it, this angle up here. That's going to be angle CED by the way of vertical angles are congruent. A very useful tool in proofs. So then finally we have arrived at enough information to support what we're trying to prove here, and triangle AEB is congruent to triangle CED by way of angle, side. Not too bad. This might be a 6-point question on the Regents exam. Now we'll try our hand with nothing given to us in terms of filling in the missing pieces. We have to fill in all the missing pieces. Alright, so we start off by whatever is given to us is going to be what we write in our first statement. So ABCD is a parallelogram. That's given. Great. We're trying to prove that the two triangles connected here are congruent to each other. So, what could we use? What could we try to sort of exploit from the fact that this is a parallelogram to get to the pieces that indicate two triangles congruent, like side, 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 side angle, side, etc. So let's say we make an executive decision to try side, side, side. Alright, so we're going to try and make that work. Let's see if we can. Alright, so what kind of things might we want to say? Well, we know that in a parallelogram, opposite sides are congruent. So therefore, I can say that AB and CD are congruent. AB is congruent to CD, comma, as well as AD and BC are congruent to each other. AD is congruent to BC. Both of them share the same reasoning, so I put them as the two statements as one line in my proof here. Alright, so next, what kind of thing might we want to say? Well, since we're trying to go for side, 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 we need a third side to be congruent to a third side. That's the connected side there. So we have a particular reasoning you might remember if I say that AC is congruent to itself. Or simply just saying AC is congruent to AC, we call that the reflexive property. Now we've established side, side, side for the triangle here. So let's write that triangle DAC is congruent to triangle BCA, and that's because of side, side, side congruence. So that one is actually pretty easy. We didn't need all 6 steps. And really we used 5 steps if you want to include the fact that we did 2 of them on this line. So there you have it. Some proofs can be pretty straightforward and easy. Not all proofs are, though. EHIJ is a parallelogram. Next is that we're going to see what other information is. So some people like to write all the given information first. So maybe I write that HP is congruent to JQ, and that also is given. So I want to mark that on my diagram as well. So HP is this little guy right there, and that's congruent to JQ, which is that little guy right there. So this guy and this guy are the congruent pieces right now. So we've written that stuff down. Good. Now we're ready to make some conclusions. So another conclusion, and don't worry necessarily about what you're trying to prove all the time. You know, kind of see what kind of things you can write down when you're first practicing proofs, and then you get to refine them. But what we're after is trying to prove that PX and QX are congruent to each other. And the way that we do most of these proofs is through proving two triangles are congruent. So we would first want to identify what triangles we mean, prove that they're congruent, and then see if what those congruent triangles can tell us can help us answer the question. So we have this triangle right here, and this triangle right here are the sort of the hidden triangles in the mix. So let's see, what can we say about this? Well, we know that from the fact that in a parallelogram, opposite sides are congruent to each other. We could definitely use that fact. Okay, so we know that GH is congruent to JI because opposite sides are congruent. And then what we can do is we can say through some subtraction, GP, it'll be congruent to IQ. GP is congruent to IQ by subtracting line 2 away from line 3, or subtracting the red piece away from the green piece, the dark green piece, the whole outside piece I'm emphasizing there. So we would say through subtraction, we were able to get GP congruent to IQ or QI. Next, we could use something else we see here. Maybe you're just looking at the picture and it pops up, oh, I see a pair of vertical angles. So maybe that's going to be key in making something work here. So we have angle GXP would be congruent to angle IXQ because vertical angles are congruent. Next, we could say that we have this angle here and this angle here congruent, but before we could say those are congruent, we would have to state that sides are parallel. So I have to make a statement about these sides being parallel. So I would say that GH is parallel to IJ because opposite sides are parallel in a parallelogram. Therefore, angle, now we could do this in a proof. You could put 1 and 2 in there as labels, angle 1 and 2. So angle 1 is congruent to angle 2 because alternate interior angles are congruent. That's enough to say. Now, I did do this with a little bit of an extra step here, but because a lot of times people will write all the stuff that's given in one statement, so I could have condensed these two here. But the next thing I would want to say is about those two triangles being congruent because we have enough evidence for that. Triangle GPX is congruent to triangle IQX by angle-side congruence. And the last piece to that would be the PX, so maybe I'll just make a 9 statement down here. Sometimes they go a little bit extra, and that's okay. So px is congruent to qx, and we would say the reasoning here is cpctc. In other words, that this is an extra side. This side right here and this side right here are extra sides in our congruent triangles, but because they're congruent triangles, those two sides have to be equal in measure. So we say corresponding parts of congruent triangles are congruent. CPCTC. So in summary, you can show that any quadrilateral is in fact a parallelogram by being able to provide evidence of one of the following conditions. You can show that both pairs of opposite sides are parallel. You can show that one pair of opposite sides is parallel as well as congruent to each other. You can show that both pairs of opposite sides are congruent. Both pairs of opposite angles are congruent. Or that the diagonals bisect each other. And one other thing is that if the one angle is supplementary to both its consecutive angles, In order, here, those are the most likely ones that you might see in a proof. Determine whether each quadrilateral must be a parallelogram by just looking at the way it's marked. So for part A here, we see that we have two pairs of opposite sides are parallel, so the answer would be yes. In the second picture, we have one pair of opposite sides congruent and another pair of opposite sides congruent, so yes, because we have two pairs of opposite sides are congruent, same measure. Looking at what this one is showing, it's showing one pair of opposite sides are parallel and the other pair of opposite sides are congruent. This is a big fat no, because if we had two pairs of opposite sides parallel and the other two sides congruent, we could possibly be describing a trapezoid. It's possible that it's a trapezoid. So it doesn't necessarily show that it's a parallelogram, because a trapezoid is not a parallelogram. In the next one, we're indicating that the diagonals bisect each other by showing congruent halves. So the answer for this one would be yes. If I show that in the next one, one pair of opposite sides are both, underlined, parallel and congruent, then the answer is yes. And finally, yes, because opposite angles are congruent. Given JL and KM bisect each other. Now, that's pretty much all I would need to do to say that it's a parallelogram in a normal proof. But this particular example wants us to show in a different way why those bisected parts make this a parallelogram. Okay, so this is more of explaining why this property works. You could just say, hey, if these guys two diagonals bisect each other, this guy's a parallelogram. Done. Call it a day. But this is an example of showing why that works. Okay, so first we're going to write down one, and that is that JL and KM bisect each other. Okay. So then the second statement I would make here is that I have congruent parts. So the fact that Kn is congruent to mn, as well as jn is congruent to ln. What we can say here is, by definition of bisection or bisect. Since we use that word up here, we're just stating that by definition of bisection, this is the conclusion we can draw. Next, I'm sneakily trying to find or say that these two triangles in here are congruent to each other. So now what I'm going to do is I'm going to go for that vertical angle action in here, call this angle 1 and 2, make my life a little easier. Angle 1 is congruent to angle 2, and that is because vertical angles are congruent. And so because of that fact and the other facts we just stated, we now have enough to say that triangle KNJ is congruent to triangle MNL by side angle side congruence. And because of that, we can make some other statements. And that would be that, well, this angle here and this angle here are congruent to each other. So I might say that, let's call this angle 3 and angle 4, make it a little easier. Angle 3 is congruent to angle 4 by our good old CPCTC. And what that in turn gives us is the fact then that these two sides here are parallel. So JK is parallel to LM because congruent alternate interior angles make parallel lines, or indicate that there are parallel lines there. And now, to make sure that this is showing you this is a parallelogram, I would also make the statement that JK is congruent to line segment LM because of CPCTC. Corresponding parts of congruent triangles are congruent. And therefore, I could say that JKLM is a parallelogram because we have one pair of opposite sides, both parallel and congruent. And that was the icing on the cake right there. That's what showed us that this was parallelogram, and that's what sealed the deal. What is a rectangle? By definition, a rectangle is a parallelogram with one right angle. But here's the thing, with parallelograms, one right angle actually implies 4 right angles. Why is that? Well, in a parallelogram, opposite angles are congruent. So if that's my right angle and indicated with the box, the opposite side's also a 90-degree angle, or a right angle. Now, another property of parallelograms is that their consecutive angles are supplementary to each other, meaning that the two angles add to 180. And what adds to with 90 to give you 180? Well, that's 90. So this angle next to the 90 is also 90, and the other one next to the 90 is also 90. So all 4 angles have to be 90 if this thing is a parallelogram with one right angle. So that's all it takes to prove something is a rectangle, is that show that it's a parallelogram and that it's got a right angle. Done. Now, something that's also kind of cool about rectangles is that because of these 4 right angles, these 4 congruent angles, we get the diagonals inside of this thing to be congruent. Meaning they're the same length. In a parallelogram in general, that's not always true. One diagonal might be longer than the other, even though they cut each other in half. In the case of the rectangle, and spoiler alert also for the square, we have congruent diagonals. So in a proof, if you're trying to show something as a rectangle, these are the things you'd need to show. Start out by going after the parallelogram proof and then adding that extra bit of flavor like one right angle or you have congruent diagonals. So here we're told that it is a rectangle. And again, like in an early example, we are just going to go through some of the properties here. So R is a right angle. R is a right angle given the fact that this is a rectangle. A rectangle is a quadrilateral that is a parallelogram with 4 congruent angles. Now RT is going to be said to be congruent to something else, and that something else is its opposite side, so EC. As well as RE is congruent to its opposite side, TC. Opposite sides are congruent. Oh, before we should have said definition of rectangle. By the way, this is again, just putting it out there, not a formal proof. We're just using the formal proof structure of statement and reasons to show the things that we could say about rectangles. RT is parallel to EC, just as RE is parallel to TC. Opposite sides are parallel. All 4 angles are congruent. So one could also say, definition of rectangle. Draw ET. Okay. Now RET, that is angle RET, is congruent to, well, this one right here. That's going to be CTE. And that's going to be our alternate interior angles are congruent. Draw RC. ET is congruent to RC because diagonals in a rectangle are congruent. Before we go into proofs with just rectangles, maybe we should also mention a couple of other quadrilaterals or parallelograms that tend to be important. And the other one would be that we'd like to talk about is a rhombus. I think that's a cool name for a shape. Rhombus is just a quadrilateral with 4 congruent sides. 4 congruent sides. So all 4 sides are equal, but it doesn't have to necessarily, a lot of people just think 4 equal sides means a square, but this is not a square. Rhombus is the more general idea, right? Now, a rhombus has 4 equal sides, so it is definitely, in the family of parallelograms, but the cool thing about rhombuses is that their diagonals are perpendicular. They form right angles with each other. And they have this property where the diagonals are going to bisect the opposite angles. We would call those angle bisectors. That is, the diagonals are angle bisectors. So not only are they perpendicular, but they're angle bisectors. So rhombuses come up quite a bit as well in quadrilateral proofs. So here, just like with rectangles, let's just go through some of the properties of rhombuses before we actually dive into the proofs. So we get that if this thing is a rhombus, then all 4 sides are going to be congruent. This would be the definition of a rhombus. Now, if we say that angle D is congruent to angle F and angle E is congruent to angle G, that's the property that opposite angles are congruent. True for all parallelograms. Draw DF, that's the diagonal here. Okay, so we'll do that. And what we have here is that GDF, this guy right here, this angle right here is congruent to EDF right here. So we see that the diagonal is cutting that angle D into two equal pieces. Call that an angle bisector. So we say that diagonals bisect opposite angles. And for the other reasoning, we could say that the other two angles over here, EFD and angle GFD, are, for the same reason, diagonals bisect opposite angles. Next, they want us to draw EG, the other diagonal, and they intersect at X, so we're going to label this X. Now, DF is going to be perpendicular to EG because diagonals, and I'll just abbreviate diags, are perpendicular to each other. So therefore, EX, well, not therefore, the last one is EX, so that's going to be from here to here, is going to be congruent to this guy, GX, and DX is going to be congruent to FX, because in this case, diagonals bisect each other, because it's a parallelogram. A square is merely just a quadrilateral of 4 right angles and 4 congruent sides. Another way to say that is a square is both a rectangle and a rhombus. So it's a parallelogram that exhibits all the features of rectangles and rhombuses. Okay, so when we're talking about squares, what properties we're looking at is, well, S is a right angle, and that's by definition of square, or even the fact that it's a rectangle, because a square is a rectangle. All 4 sides are equal, so that might be something by definition of, yeah, you know what, I'm not going to say square in the first one here, I'm going to just use rectangle, and that'll be the first reason there. Well, what an angle, and then we have definition of rhombus for the next one. Alright, and then the 4 angles are congruent to each other. That's definition of rectangle. Okay, and so now draw the diagonals. And we know that the diagonals are perpendicular to each other in a rhombus. So SU is perpendicular to QA. SU is also congruent to QA because in a rectangle. So first of all, we're going to say that diagonals are perpendicular and diagonals are congruent. One from the rhombus and one fact from the rectangle. So angle ASU, that one, is congruent to QSU. And that would be because of the rhombus, we have diagonals are opposite angle bisectors. And that would be the same reasoning for these two guys. So let's challenge ourselves and do a proof with one of these. So example 1 here, ABCD is a rectangle. And that's given. M is midpoint of AB, also given. Because A is the midpoint of AB, the next statement I'm going to make is that AM and BM are congruent. By definition of midpoint. Good. Now we're going to try to prove that DM and CM are congruent to each other. All right, that's our goal, and we're going to do that through the triangles. All right, since this is a rectangle, I know that these two angles are going to be right angles. So what I'm going to write down next is that angle DAM and angle CBM are right angles, and that is because of the definition of rectangle. Beautiful. And now, because of the fact that this is a rectangle, we also know that these two sides are congruent to each other. So I'm going to say that DA or AD is congruent to CB or BC, and we're going to say that that reasoning there is because opposite sides are congruent. That is in our rectangle that was given to us. So lastly is that we now have the triangle DAM is congruent to triangle CBM by way of, oh wait, we can't say that just yet. Back the truck up. We have to say that the right angles, angle DAM is congruent to angle CBM because all right angles are congruent. Now I can say that triangle DAM is congruent to triangle CBM because of side angle side. Now I can finally say that DM is congruent to CM because of CPCTC. So you have to create a little story with your proof, a line of reasoning. If this happens, and this is also true, then this is true. Given rhombus, RHOB. So rhombus, RHOB. Given. Prove that angle HSR and angle HSO are congruent to each other. Okay, so keep in mind those angles that I have marked there are what we're after. So because of the fact that this is a rhombus, what do we know and what can get us there? Well, what we're going to try and do is we're going to try and prove that two triangles are congruent somehow. Alright, so first things first is why they tell us it was a rhombus. Well, it's to use one of the properties of rhombuses. And the property I'm going to go for is that all four sides are congruent. So the ones that I really need are RH and HO. So RH is congruent to HO. Okay, RH is congruent to HO because of the fact that it's by definition of rhombus. Okay, and we can also say that RS and OS, RS is congruent to OS because diagonals bisect each other. So that would make congruent pieces. So since we know that this is a rhombus, it's also a parallelogram, which means the diagonals bisect each other. Alright, and another thing that we know is that, so you can label this angle here 1 and this angle here 2 and state that angle 1 is congruent to angle 2 because, well, can we say that? Well, maybe so we may not be able to say that exactly, but let's go back, let's backtrack here, think about that. Maybe we can't say that, but maybe we can say that these two angles, 1 and 2, are congruent, and that there's a reason for that one. That would be that diagonals bisect opposite angles. So angle 1 and 2 will be congruent to each other. Those pair of angles are congruent. The other pair are not bisecting, not coming from the same bisected angle. Okay, so now what we've done is we've established, well, what have we established here? This is why I did this, because sometimes a proof you have to go through it. If I look carefully on the triangle, what I've established is angle, side, side. Now, angle, side, side is not a valid reason, so I actually went about this a way that took me to sort of a dead end. I didn't really want to use those angles and those combination of sides and angles. So how might I adjust this proof? So one of the reasons that we do proofs is to see maybe where we might see adjustments. Okay, what do we actually can we get out of this? Okay, so one of the things we can get out of this is instead of saying that angles 1 and 2 are congruent to each other, because that really doesn't help us out. Alright, what we're going to do is instead use a different property. We're going to say that diagonals are perpendicular. Alright, so that we can say that, where are we here? We have that angle RSH and angle OSH are right angles because diagonals in a rhombus are perpendicular. And now this is where we see one of those obscure proofs come out, hypotenuse leg. Which is typically known as HL. And that's because we have two right triangles. So triangle RSH and triangle OSH are congruent to each other by hypotenuse leg. We have one hypotenuse congruent to another hypotenuse and the leg congruent to a leg. And because of that, we can then make some statements about what we wanted up here. And that is that those two angles that we just mentioned, RSH, is in fact going to be congruent to the other one. So I actually didn't really need to say that, this part of the proof actually, because I could have just went right from here to here and said angle HRSR is congruent to angle HSO because all right angles are congruent. Typically, we would think about that being like a CP-CTC type of reasoning, but here I didn't actually need it. So this actually that I circled here was something a little extra, but that you might see in another proof. And I just wanted to bring it up for HL purposes because you need to see sometimes the hypotenuse leg reasoning. A trapezoid. A trapezoid is a quadrilateral with one pair of opposite sides parallel and the other pair are not. Okay, so TR is parallel to AP is what we would say is the definition of a trapezoid. So then angle T, will be supplementary to certain angles. Okay, so angle T will be supplementary to this bottom angle. So that's angle A. And angle R will be supplementary to angle P. Okay, so you have to see that we would call these guys in here consecutive angles or supplementary. But it's only along the non-parallel sides, those two angles there. Okay. So let's take a look at what an isosceles trapezoid has to offer. That just simply means the non-parallel sides will be equal in measure or congruent. So RO is parallel to QP or PQ. Okay, RO is congruent, so this should actually say RQ. I think they have a little typo there. RQ is congruent to OP. We'll fill in the reasons a little bit. Angle O is going to be congruent to angle R in the case of the isosceles, as well as angle Q is going to be congruent to angle P because of the fact that they have these parallel lines involved. So, definition of trapezoid. Congruent parts are definition of isosceles. These are called base angles are congruent. QO is congruent to RP. Diagonals are congruent in the isosceles case. So let's just make the statement over here. Angle QOR is congruent to angle, so Q to O to R is congruent to OQP. Alternate interior angles are congruent. And the other set of angles, let's just call them angles 1 and 2, make things life easier. Angle 1 is congruent to angle 2 for the same reason we just stated there. Isosceles trapezoid. Let's do two final proofs with quadrilaterals. So in this particular one, quadrilateral ABCD is given. So 1 ABCD is a quadrilateral. I don't pre-number my proofs because I don't know how many steps it's going to take. Diagonals AEFC is drawn there, and there's a couple of perpendicular statements, so I'm just going to include everything into one statement for the given. So I'm just going to diagonal AEFC parenthesis comma DE is perpendicular to AC, indicated with the right angles. BF is perpendicular to AC, and AE is congruent to CF. That I will have to mark. And DE is congruent to BF. Okay, so that's all the stuff that's given there. We want to prove ABCD is a parallelogram. Okay, so the way that we're going to go about this is we're going to go after these two sides. And because they're connected to these two triangles, we can do that. Okay, so 2, what are we going to say? We're going to say that that this angle 1 and 2 here are, well, we know that those are right angles, so we're going to say that 1 and 2 are right angles by definition of perpendicular. Next, we're also going to say that angles 1 is congruent to angle 2 because all right angles are congruent. 4. Next, we're going to say that the two triangles are congruent by side angle side. Triangle AED is congruent to triangle CFB by side angle side congruence. And because of that, we're going to be able to say AD is congruent to BC by CPCTC. By the way, we could also say that angle 1, I'll call this guy angle 3 because we used 1, and angle 4 over here are also congruent by CPCTC. Whoops. Try that again. Angle 3 congruent to angle 4 by CPCTC. And therefore, we can say that side AD is parallel to side BC. Okay, because congruent alternate interior angles imply parallel lines. And then finally, which I don't have enough room on the bottom here to, number 7 would be that ABCD is a parallelogram, and my reasoning would be that we have one pair of opposite sides, both parallel and congruent. That establishes it as a parallelogram. Given ABCE is a rhombus, and that FAB is congruent to DCB, okay, prove that FE is congruent to DE. Okay, let's get rid of some of that marking. First statement is that ABCE is a rhombus. A couple things I can say about that before I go to my next given. Alright, well, conclusion here is that this side and this side are congruent to each other. So AE is in fact congruent to EC. Okay, by definition of rhombus. Next, we're going to mark up those angles that we just mentioned. So FAB and DCB are congruent. Which would make then well, why would you think they told us those are congruent? If I investigate these two triangles, here and here, we'll be able to get after what we need. So what I really would like to say is something about this angle here, I'll call it angle 1, and this angle up here, angle 2. Now, because of the fact that ABCE is a rhombus, we can say that, let's call this angle 3, I'll call this angle 4 for instance, We know that angles 3 and 4 are opposite angles that are congruent. Because of the fact that it's a rhombus. Now, if I were to subtract angle 3 from angle FAB and angle 4 from DCB, what I'm going to get is angles 1 and 2. So angle 1 is congruent to angle 2 by subtraction. Alright, so now, we can also establish that since we have some lines here that form a pair of vertical angles up here, I could say that angle FEA is congruent to angle CED by way of vertical angles are congruent. Now I have enough to say that triangle FEA is congruent to triangle CED by way of angle side angle. And that helps me conclude that side FE is congruent to side DE by CPCTC. And so we see again, even if it's a quadrilateral type of proof, triangle congruences always seem to creep up inside. And CPCTC is often used after we found two triangles are congruent. So we go through that middle part of doing that so that we can use CPCTC. Thanks for hanging in there. Remember, you have to persist to get through a proof, so it takes patience. Good luck.